Welcome back to the online course Road, Subgrade, and Pavement Engineering. My name is Peng Li. Let's continue on the topic of concrete pavement. Previously, in part 1, we already talked about what is a concrete pavement, types of concrete pavement, and associated distresses. In this section, we're moving to the concrete pavement stress analysis. In this section, we will learn basic assumptions for concrete pavement stress analysis, load-induced stress, and temperature-induced stress. In the real world, things are complicated, especially when we do stress and strain analysis. We have to make assumptions to simplify the condition. When we make assumptions, we need to consider the characteristics of concrete pavement itself. First of all, as we mentioned in previous section, concrete surface has great stiffness and takes the majority of loads. Second, in terms of traffic loading effect, the focus of stress analysis is on concrete slab internal stress calculation and analysis. So therefore, we use the theory of thin plate system on elastic foundation. In the following slides, there are a lot of equations. I will try my best to make them simple. Concrete slab is very thin plate, and the strain in z direction is so small that it can be ignored. Using equation to illustrate this idea is shown here. Sigma z is the partial derivative of w respect to z. W is the displacement function in z direction. Because it equals to 0, which means the w is only the function of x and y, nothing to do with the z. Next, normal vector of the natural x are always perpendicular to the natural surface, which means no shear strain in horizontal directions. By definition, the shear strain is shown here. Because it's equal to 0, therefore, we could get the expression of u, which is the displacement function in x direction. And similarly, we could also get the expression of v, the displacement function in the y direction. Next assumption is no horizontal displacement within the natural surface, which means when z equals to 0, u equals to 0. Then we could simply conclude that function f1 equals to 0, and then it can be removed. So the function of u can be further simplified as this. Similarly, when z equals to 0, v also equals to 0. The function of v can be also simplified. So it's not that hard, right? Now we have simplified functions of displacement in 3 directions: w, u, and v. So by definition, we can get expressions of strain component and stress component here, represented by displacement of w, u, and v. Next, we move to the load-induced stress analysis. Concrete pavement models can be classified into 3 categories, as shown in this figure. There are single-layered plate system on elastic foundation, 2-layered plate system on elastic foundation, and composite plate system on elastic foundation. Among the 3, we are only going to talk about the stress analysis of single-layered plate system in this lecture. Single-layered plate system is illustrated in figure A. It could be a concrete slab on granular base or subbase, or concrete slab on the existing asphalt concrete. Two-layered plate system is shown in figure B. The base could be HBM base, HMA base, or the existing concrete base. Figure C and D show the composite plate system. It could be a composite surface or composite base. You can find detailed descriptions in this figure or in the design specification. The cement concrete slab is assumed to be homogeneous and to have uniform elastic properties with vertical subgrade reaction bearing proportion to the direction. There are three typical locations to analyze stress status of a concrete slab: internal, edge, and corner. Please be aware that in the center and on the edge of the slab, the bottom of slab is in tension. Meanwhile, at the corner, the top of slab is in tension. We use the three equations to calculate stress at the three locations respectively. These are simplified equations, and there are other versions of simplification. The calculated stress are in the unit of 0.1 megapascal. In the equation, H is the thickness of slab in centimeter, P is the wheel load in kilogram, A is the radius of the wheel load in centimeter, L is the radius of relative stiffness in centimeter, and the equation to calculate is shown here. B is the radius of resisting section in centimeter, and the way to calculate it is to use this equation. Next, let's move to the thermal stress. As we mentioned before, during the day, when the temperature on the top of slab is greater than that at the bottom, the top tends to expand with respect to natural X, while the bottom tends to contract. However, the weight of slab restrained from expansion and contraction. Thus, compressive stress are induced at the top, tensile stress at the bottom. At night, the situation reverses. If the slab is completely restrained and prevented from moving, the maximum strain is calculated as this equation. It is a function of change of temperature and alpha, which is the coefficient of thermal contraction or expansion. The stress in x direction due to bending in the x direction is calculated as this equation, and the stress in the x direction due to the bending in the y direction is calculated as this. For an infinite slab, the total stress in x direction can be simply obtained by adding previous two equations together. But for a finite slab, the situation is slightly complicated. We still add stress caused by bending x and y direction together, but coefficients cx and cy are added. Cx and cy are called the correction factors for a finite slab. To determine the value of Cx and Cy, we use this chart on the right-hand side. The curve is a function of length in x or y direction over L. As we mentioned before, the L is the radius of relative stiffness. And that's all for today. Thank you.